Today we will continue our discussion of SN2 reactions by talking about some of the variables that might be involved. And last time we talked about, here in our generic SN2 reaction, we talked a little bit about the nature of the nucleophile. Of course, the nucleophile's job is to provide the electrons that are used in the new bond at the carbon, and consequently nucleophilicity is tied to the nucleophile's ability, driving force, desire to share electrons, which is tied to its ability to accommodate them. In other words, the happier the electrons are on the nucleophile, the less inclined it is to have to share them. We also talked about the nature of the leaving group, and the role of the leaving group is pretty much exactly opposite of the role of the nucleophile, and that is to leave with a pair of electrons. And so consequently, the best leaving groups will be those that can accommodate this pair of electrons most effectively. Exactly the same kinds of factors that influence nucleophilicity also operate on the leaving group. Today, we're going to talk a little bit about the nature of the things attached to carbon. That turns out to be fairly straightforward. And then we're going to spend some time today and also into Friday talking about the nature of the solvent and how it influences that. So everything we're going to do today is going to be in our lecture supplement, so we're going to start on page 5. All right, so the question we're going to ask then is, what happens when I change the nature of the things that are attached to the carbon? Does that matter? We can think about this by looking at the transition states that would be involved with the different R's attached, because those R groups, it's the transition states that are going to control the rate. So if we look at any one of these transition states, any one of these 4 that we have here for different number of R groups attached to the carbon, we can think about why these things are energetically expensive to begin with. What is one of the principal reasons why, let's say for this methyl iodide reaction that we have on the top, what is a principal reason that this structure, the transition state, is higher energy than the reactants? Imagine this carbon is your dorm room, right? Your dorm closet. And you already have 4 people living there, right? There's you, and there's your friends. Now somebody else moves in. How do you feel about that? Somebody every quarter says, "Oh, that's just the norm. I don't feel any different." No, you feel crowded, right? They're moving in. How do you express your discomfort at being crowded?
You leave.
Right? You leave. There you go. That's one way to look at it. Suppose you have no other place to live, though, right? But so how do molecules do that? When a molecule becomes more crowded, when you shove more stuff into that space, how does a molecule respond to that? What property of a molecule might change when it's more crowded? Energy, potential energy. You take more stuff and shove it in a smaller space. It doesn't like to be there. So part of the way the molecule responds to this is by having these groups, as the nucleophile moves in, of course these groups move away, but this costs energy. That's why one of the reasons why transition state is higher energy than reactants or products. Now that repulsion comes from, in this case, the nucleophile, that's what we have in orange, interacting with these guys through van der Waals repulsions, electron repulsions. Stands to reason that the more of those repulsions there are, and or the more severe they become, the higher the energy price. In other words, if you're moving into a dorm room where there's 4 other people and they don't have very much stuff, they go, wait, I've got my Chem 14D thinker, that's all I need, so I've eschewed everything else in my life. I have no clothes, no bed, no iPhone, nothing. All I need is my reader. Then you'll think they're crazy. As opposed to a place where you move in and the guy goes, well, we all have our own plasma TVs and our iPhones and our big stack of books, right? This is all the books I bought just for my GE course last quarter that I had to read, all this other kind of stuff, right? There's more junk in the room, it's more crowded. So it's the same thing here. When the R groups become bigger, when the things attached to that carbon become bigger, the effects, the repulsion just becomes greater. So in the first case, we have a methyl group, 3 hydrogens. That's about the least amount of repulsion you can get. The second case, we now have 2 hydrogens and another methyl. In other words, I've converted this hydrogen to a methyl group. Well, bigger group, more repulsion. Right, remember we learned that way back when in 14b, when you talk about conformations of molecules, bigger things have a greater preference to be in a particular position because there's more repulsion. If I have now 2 methyl groups, more repulsion, 3 methyl groups, even more repulsion. And if I was to make the size of the groups bigger, if I was to have a tertiary butyl group instead of one of those methyl groups, that would be even worse. So as the number and or size of the groups goes up, the repulsion becomes greater, and it costs me more energy. More energy for the transition state means what in terms of relative rate? It means slower. All right, so let's go through this sequence. In the top, the case where R equals methyl, so there's the carbon with the 3 hydrogens attached. We're doing RBr here, so there's the bromine leaving, there's the iodine coming in. Where we have this minimal repulsion, that has the least amount of repulsion, so this is going to be the fastest case of all of the ones on here. And as we increase the number of R groups, replacing hydrogens with bigger things, it becomes slower and slower. As we go down here, this is slowest. Now, it's going to be convenient to talk about the number of carbon groups attached to the carbon that bears the leaving group. So we can talk about this effect instead of saying 1 methyl group, 2 methyl groups, etc. Because it turns out to be, the number of groups attached turns out to be a useful idea across the board. When the carbon that's of interest, in this particular case, the one that bears the leaving group, when the carbon of interest has no other carbons directly bonded to it, we call it a methyl carbon. In this particular case, it happens to have 3 hydrogens, so it looks like a methyl group. But if it was, let's say, 3 chlorines attached instead of 3 hydrogens, we'd still call it a methyl carbon. If there was 1 carbon group bonded to it, that's this guy, then we call that primary. If there's 2 carbon groups here, and it's kind of buried in the back, but here, that's secondary because there's 2 groups attached. And then 3, 1, 2, 3 is tertiary. Now, if you have 4 attached, it's called quaternary. We don't run across those too often in this course. We do run across them occasionally. But a quaternary carbon with a leaving group would be of no interest in this particular course. Actually, it would be a bit of an embarrassment if you drew a quaternary carbon with a leaving group. And while I draw it, you can figure out why that would be. Let's see. Let's take 4 methyl groups to make it quaternary. So that's quaternary, 4 things attached. And then I need a leaving group. You can see why that would be a problem. I hope you see why that's a problem. All right. So we're going to worry about these. So basically, as the degree of number of things attached goes up, the rate goes down because of this crowd. And we call this phenomenon steric hindrance because it's steric in nature. Steric means it has to do with the size of the groups involved. And, well, it's hindrance to backside attack. And steric hindrance is a phenomenon we're going to see in a lot of places, not just SN2 reactions, but pretty much any time where something has to approach something else. The more crowding there is, the slower it tends to be. So in the very bottom, we have our reaction rate trend that we can fill out then. Methyl is faster. Methyl is faster than primary. Primary is faster than secondary. Secondary is faster than tertiary. As a matter of fact, tertiary is so difficult to do. It is so difficult to get a nucleophile, even a small one, into that space when there are 3 alkyl groups or other things already attached. Maybe you want to put several, is slower than. It's so slow that tertiary is not just slowest. Let's replace slowest with something else. Let's replace slowest with NR, which means no reaction. SN2 reactions on tertiary carbons are virtually unknown. There are 1 or 2 of them that are, we kind of figure they're SN2 reactions. But beyond that, it's just so crowded, they're virtually unknown. So methyl, we can do plenty of those. Primary, okay. Secondary, yeah, okay, we certainly do plenty of those. But tertiary, that's out of the question. All right, now, let us shift, while we're on our lecture supplement, to the 4th factor, and that is solvent effects. How does the solvent play in all this? First question we have to ask is, why should we bother? Is solvent just something we could ignore? Is it just there to be pretty or to serve a practical role and not an important role? The answer is, well, it does serve an important role. Most of the time when we think about a solvent, of course, it's the stuff we put in to dissolve stuff. And maybe that's the only role it serves. You're familiar with solvents, though. How many of you had coffee this morning? Or tea? Or Red Bull? Or Monster? Or any liquid that had stuff dissolved in it that was a drug? Caffeine is a drug. My drug of choice can be your drug of choice, too. The water in there is a solvent. It dissolves the stuff. Now, if you just ate the instant coffee right out of the container, right? A spoonful of instant coffee, a spoonful of sugar, a spoonful of powdered creamer, and you're ready to go. Well, you didn't have solvent. But in the case of coffee, the solvent, the water is there to dissolve everything. Now, in the case of coffee, it makes it more pleasant. We're not so worried about pleasant when it comes to reactions, but why might we have a solvent, the stuff that dissolves other stuff, why might we have that in an organic reaction? There's a slew of reasons. Some of them are, perhaps one of the most important is so that they can dissolve the reactants so that they can mingle. Now, mingling is important because remember that reactions require the reactants to, when they bang into each other, they have to have the appropriate energy plus the appropriate orientation. And if they're solids, they can't, the atoms don't, the molecules don't have an opportunity to move around and find different possibilities to bang into each other. So if you mix two solids, often reactions don't happen that would happen otherwise. Let me convince you of that. Here in the middle, where it says demonstration, obviously I'm going to do a demonstration. How many of you know about Alka-Seltzer? You know, plop, plop, fizz, fizz? No, it's not finals week yet, so you probably don't know about Alka-Seltzer. Alka-Seltzer is this stuff, which is basically citric acid, which is a solid acid, and sodium bicarbonate, which is a solid base. If you mix them together and you plop them into the water, they go and they give off carbon dioxide, and you drink that, and you're supposed to feel better. Well, it doesn't do anything when it's a solid, but it does something when you add it to the water. Let me show you that. Here we have sodium bicarbonate, solid. That is a base. Here is citric acid. It even says anhydrous. Citric acid, an acid. What happens when you mix an acid and a base? They don't blow up. Maybe when you took general chemistry in the lab, they blew up. But acid and base react, right? I'm going to push it over here because maybe it will be violent. I'll put it right in. This is like a How many of you ever gone to a Gallagher concert? You know about Gallagher? He's the guy who smashes fruit with a big hammer. All right, so if you're sitting in the front, here we go. You ready? That's a base, that's an acid. They're not doing anything. They're just going to kind of sit here. That's disappointing. Well, that's solid Alka-Seltzer, right? Doesn't do anything until you put in a solvent, water. So now they can react. Why? Because they can dissolve, find the appropriate orientation, and actually react. So what they're doing here is, when we mix them dry without a solvent, they don't do anything, NR. But when you add the water, then they can react, and you get, among other things, carbon dioxide and the salt that's produced in this. So here's a great example of how solvent can help the reaction happen. But there's other things that solvents might do. For example, if you have a reaction which is highly or even moderately exothermic, if it gives off heat, you might want to control that, because after all, as it's generating heat, that heat, if it stays in the reaction, what happens when you add more heat to a reaction? What happens to its rate? It goes faster. And when the reaction that's already exothermic and giving off energy goes faster, it gives off blank energy. More energy. And that more energy stays in the reaction and makes the reaction go even faster. So it can run away from you. So you might put a solvent in. It doesn't actually necessarily change anything about the reaction, but because the solvent has a much larger amount of mass in there, more stuff to absorb energy, and consequently the temperature doesn't go up as quickly, and you can control the rate. So that's something useful. Sometimes when we run a reaction, we want to take advantage of solubility to drive an equilibrium. So there might be a circumstance where the reactants are soluble, but one of the products isn't. And so as the reaction proceeds, the product precipitates out and it can't come back in the equilibrium. That's just one of many, many. I mean, we could probably write a dozen other things that we might pick a particular solvent for to do a reaction in the laboratory. Now, we want to talk about solvent effects on the SN2 reaction rate. Now, we're thinking about this from the viewpoint of not only understanding a little bit of theory, but kind of from a practical point of view. If you are going into the laboratory and you have to do an SN2 reaction, let's suppose you've graduated from UCLA and you are now employed by SN2 is us. Okay? So you're going to work for this company, and your job is to do SN2 reactions. You have a whole bunch of different solvents you can pick. Water, alcohol, gasoline, what do you use, right? Certain things will make the reaction better, slower, whatever. So that's what we want to talk about. You also might say, well, I'm in 14D. I'm a pre-med. I really don't care about reactions in the laboratory, other than the extent that I have to get an A in this class. You know, because I'm never going to go to the laboratory and run a reaction. I'm interested in this. Well, guess what? This is full of solvent as well. There's water in you. Enzymes, the active site of an enzyme where a reaction occurs, you can think of the enzyme as the solvent. So the nature of the enzyme can even influence the rate at which the reaction occurs. So these are all reasons that we might be interested in this idea. So let's talk about solvent effects on SN2 reaction rate. Now, of course, reaction rate is tied to energy difference between reactants and transition state. So let's ask a very general question. What happens if we were to change a solvent? Well, solvents interact, we call it solvate, interact, are around the reactants in there, and also the transition state as well, and the products. How the solvent interacts with them will control their energy. Sometimes the solvent makes something more stable, sometimes it makes it less stable, sometimes there's really no significant change in energy at all. So let us imagine that we start with a case where we're going to call this solvent A. That's what's in the solid line here. And let's just say, for the sake of this particular reaction, it's exothermic. That doesn't really matter. And there is its energy of activation. So it's the solid line. Now let's suppose we compare that to another reaction in which we have solvent B. And solvent B, for whatever reason, we'll talk about why in a second, for whatever reason, solvent B provides a lot of stabilization for the reactants. So their energy goes down significantly, but doesn't do really much for the transition state. So the reactant's energy relative to the solvent A has gone down a lot, but only a little bit for the transition state. All right, what's happened to the rate? Now, it's true that solvent B, the dotted line, has a lower transition state structure energy. That is true. But it is not only the energy of the transition state that controls the rate. Rate is controlled by a delta G, not just a G. It's controlled by a delta G. It's the energy difference between the reactants and the transition state. So if you want to compare the rate of these two, look at the magnitude of the energy of activation here. In solvent A, it's that big. And in solvent B, it's gotten bigger because we lowered the transition state energy a little bit, but the reactant energy a lot. So which of these two, where we have energy of activation for B is greater than energy of activation for A? So what happens to the rate? Is reaction B faster or slower than A? It's slower. So here solvent choice has influenced the rate of the reaction. And we can make another kind of scenario where instead of changing, so we're going to now take solvent A and compare it to C. And in this case, in C, we don't have much additional stabilization for the reactants, but we have a lot of stabilization for the transition state. And so the energy of activation for solvent C is lower than it is for A. Energy of activation for C less than A. So what do we know about rate? Well, lower energy of activation, faster rate. So what's happening is by the nature of the solvent is influencing the rate of the reaction. If this was an enzyme, maybe the nature of how the enzyme interacts with the reactants may influence the rate of it. So what we would like to know then is what things are involved in this interaction? What provides stabilization? To what extent is that stabilization? What kinds of solvents might we think about, etc.? So let's start by asking on page 7, exactly where does this stabilization come from? What is involved? And the answer to that is we really already know. Because when a solvent, for the most part, when the solvent interacts, is around reactants, let's say a nucleophile, it's not forming a covalent bond to that nucleophile, unless the solvent's actually involved in the reaction. That happens in some cases. The interactions they have are temporary and non-covalent. We know about non-covalent interactions. This is part of why we talk about it in Chem 14C. So remember all the kinds of forces we talked about. We talked about, and these were all, for the most part, electrostatic in nature. And we talked about dipole-dipole, ion-dipole, hydrogen bonding, London forces, and so forth. If you don't remember those, good idea to go back and review them. But these forces are all electrostatic in nature. And the ones that I have listed here, the 4 that I have listed, are the most important for solvents. Other things can matter, but those are the ones that are most frequently involved. Now, and of those, the London forces, we're going to ignore in our simple introduction because they're generally pretty weak, they're generally insignificant, and they also tend to be pretty much equal between all the kind of things involved. So these ones are going to be really the most important. Now, How does this kind of interaction look? Imagine we have the green circle here in the middle. That's F minus. That's fluoride ion. And if I take that and dissolve that in ethanol, CH2 or CH3CH2OH, there must be some sort of attractive non-covalent force because it dissolves. Remember, that's how dissolving works. You've got to like the solvent to be dissolved in the solvent. It's like if you want, I just thought of this metaphor, see if it works. Imagine you want to join a club on campus. It's kind of an exclusive club. Do they like you? Then they let you join the club. You dissolve in them. If they don't like you, they say, you ain't coming into our club. They exclude you. You're not miscible. You don't dissolve in the club because they don't like you. There's no attraction there. No? Doesn't work? Okay, forget it. So, but for dissolving to occur, there has to be some attraction. So here's our F minus. Now, what would F minus be interested? Negative charge here would be interested in ethanol. Well, here's ethanol. CH3CH2OH. Now you might think that non-covalent interactions are based on charges. All right, there's a negative charge on the fluorine, and this is an oxygen, and that's a hydrogen, so there is a delta minus delta plus arrangement on that OH. Oxygen being more electronegative than hydrogen puts the delta plus on the hydrogen. And that is why in this particular drawing, the hydrogen is pointing in towards that fluorine. Delta minus on hydrogen is attracted to the F minus. It's hydrogen bonding, it's ion dipole. You can use either of those words to describe it. And as a matter of fact, the 4 ethanol molecules here are all attracted to the fluorine in that, the fluoride ion in that same way. Now, I do not mean by this drawing that it's only 4 ethanols around a fluoride, and it's organized, and it's static in nature. None of those are true. Number one, it's probably more than 4 ethanols. It's probably a dozen or 15 or something like that. Number two, it's not nice and neat and organized. They're not all equally spaced out. They're kind of crowded and chaotic. As a matter of fact, there's not really a lot of space between the solvent molecules at all. Number three, it's not static. If you sit here and look at this for 5 minutes, it's not going to change. The nature of this surrounding of the thing that's being dissolved by the solvent shell, the shell of molecules around it, the solvation effect, it's dynamic. Ethanols are coming in and out, etc. It's like a party where there's one guy in the middle and everybody's coming in, they talk to him, and then they leave and so forth. Now, what kinds of properties do we need to think about when it comes to solvents? We understand here a little bit about how the solvent surrounds the thing that's forming the solvent shell, but what kinds of properties do we look at? When we're identifying a solvent, looking at its structure and saying, how does this guy interact with the stuff that's dissolved? The nucleophile, the electrophile, the transition state, whatever. What kind of things do we look for? There are fundamentally 2 things: dielectric constant and proticity. Let's start with dielectric constant. Dielectric constant, we use the little squiggly there for our symbol. That is, according to physicists, essentially the ability to insulate opposite charges. Now, that's not a terribly useful term for us. A better way to think about it for us is simply a measure of how well opposite charges like each other. How much charge does the solvent have? So if the molecule in question has lots of areas of charge, most of the time it'll be deltas, but sometimes it's full pluses and minuses, and or those delta charges have a larger magnitude. Both of those things, more charges and or larger magnitude, make for higher dielectric constant, what we call more polar. Now, why is that important? Well, if the thing that we're interacting with, let's say F minus, which has a full negative charge, is going to like a solvent that has lots of areas of positive charge, opposite charges attract. It's also going to like those areas of positive charge if the charge is more intense. Remember, the stronger the charges are, the stronger the attractive force. And the stronger the attractive force gives you more stabilization. So in other words, F minus, for example, is going to be happiest in a solvent that has lots of positive charge that it can point towards that fluorine. So that's the kind of thing where dielectric constant matters. So higher dielectric constant, greater number and magnitude of charges, both pluses and minuses, by the way, and that means stronger attraction to solute, especially if the stuff that's dissolved, the solute, has charge. If the solute isn't charged, if instead of being F minus, this is a molecule of methane, for example, methane really doesn't care that much about the solvent around it because methane has almost no charges. It just has very, very little to interact with the solvent. So strength of the interactions, we talked about full positive charge is bigger than deltas, and that's bigger than neutral. The greater number, and how do I determine dielectric constant? Now, the best way to do that, to see the higher the dielectric constant, is to simply look at the structure of the solvent and make a judge as to how many polar bonds there are relative to nonpolar bonds and how polar those bonds are. So in other words, the more areas of charge and the less areas without charge makes for a higher dielectric constant. So here's an example of that. Methanol, CH3OH, has a dielectric constant of 33, which, by the way, is kind of middle of the road. The ranges are anywhere from about 0 to 80. We'll look at some numbers in a second. Compare that to ethanol. CH3CH2OH has a dielectric constant of 25. So we say that methanol is more polar, has a larger dielectric constant. Why is that? Well, they both have the same number and magnitude of polar bonds. Both of those molecules, because they have the same functional group, an alcohol, they both have a polar CO bond and have a polar OH bond. And the magnitude of the charges are the same. Same delta minus on oxygen and so forth. Methanol has 3 nonpolar bonds in it, the CH bonds. So 3 polar, 3 nonpolar. The ethanol has 3 polar, the CO and OH, but it has 1, 2, 3, 4, 5, 6 nonpolar bonds in the CC and CH bonds. So the ethanol has a greater percentage of its structure as nonpolar bonds. That's the way to think about it if you like. And hence, greater amount of nonpolar bonds, lower dielectric constant. Ethanol isn't as good as interacting and stabilizing with things that have charge. Ethanol not as good at that as methanol is. So if I took F minus and threw it in a beaker of methanol and threw it in a beaker of ethanol, it's going to be happier in the methanol because it's more polar environment. Now we make a kind of arbitrary demarcation about polarity. And that is if the dielectric constant's greater than about 20, we call it polar. And if it's less than 20, we call it nonpolar. That doesn't mean that there is a sudden sharp change in properties at dielectric constant 19.9 versus 20.1. It simply is a convenient place to make a demarcation. When we look at solvent structures, specific structures in a few minutes, you'll actually see why we make the demarcation there. Now, the other factor to look at is proticity, and that is the ability to donate a hydrogen for a hydrogen bond. And review Chem 14C if you forget how to do that. But basically, that means most common hydrogen bond donors are NH and OH bonds. Remember, there's lots of those in protein and DNA and things like that. But as it turns out, for the common solvents, we don't have to worry about NHs. So really, when we're talking about proticity, ability to hydrogen bond, we're looking for OH groups. Now, if the solvent has an OH group, if it can share a hydrogen through hydrogen bonding, if it's the hydrogen bond donor, we're not talking about the acceptor, we're talking about the donor end here. If it has an OH, we call it protic. And if it doesn't have one, if it's not protic, we call it aprotic, not protic. So like remember chiral and achiral? This is protic and aprotic. Here's an example. Ethanol has an OH group on it, so it's protic. Dichloromethane, also called methylene chloride, CH2Cl2, does not have an OH group, so it's aprotic. Now, you might come to the conclusion that because hydrogen bonding involves charges, remember you have to have a big delta plus on the hydrogen of the hydrogen bond donor to do hydrogen bonding, you might say, aha, that's charge, and therefore a protic solvent, because it has an OH and polarity, must also be polar. That's not true. Imagine I have an alcohol that has 8 carbons out here, so octanol, 8 carbons with an OH on the end. That's protic, it has the OH. But because it's got so much more CC and CH bonds than it has polar bonds, we would call that nonpolar. All right, now on the next page, 8, we have some solvents to look at. This is a list of it's not a complete list, but it's a list of some of the most common solvents that we might see in organic chemistry, including the 4 or so that by far we see the most use in SN2 reactions. We have divided into the name, some of these have abbreviations, the structure, whether or not it's protic, and what its dielectric constant is. And I've made that arbitrary division between polar and nonpolar based upon that dielectric constant. So let's start with water. Of course, we know the structure of water. It's definitely protic. Water is nothing but OH bonds. Its dielectric constant is 80. That, my friends, or my enemies, or whatever you are, we're neither. Well, we're friends, of course. We're not enemies. We're not in competition here. Colleagues, students, whatever you are, folks out there, huh?
You people.
You people. Yeah, okay, that's fine. You people. I'm here to tell you, you people, that this is a large dielectric constant. Water is about as polar as you get. 80 is the high end of the scale. You put something like F- in water, it really can't get much happier. Next on our list here is DMSO, dimethyl sulfoxide. It's a sulfur-oxygen double bond with two methyls on it. And does it have an OH group? No, so it's aprotic. It is not capable of donating a hydrogen through a hydrogen bond. It's still pretty polar, not as polar as water. Why is that? Well, on its surface, you say, okay, this makes some sense. It's got one polar bond in it, the SO double bond, and everything else that's present, all 6 of those CH bonds, and the 2 carbon-sulfur bonds are nonpolar. Remind yourself, what's the electronegativity of sulfur? Hint, it's the same as 2 other elements that we talk about. If you forget your electronegativities, anybody remember what the mnemonic is you can use? The Fackelbernisch? Actually, it's Fackelnbursch. It sounds like some Scottish dish. You know, you serve it on the side with haggis or something. It's the sequence of decreasing electronegativities. It can be useful, but carbon, sulfur, iodine, all about the same at, what's the number? 2.5. So the carbon-sulfur bonds here, not very polar. So in other words, it has polarity in this portion, but not out here, not out here. So that's why its dielectric constant is less. Then there is N,N-dimethylformamide. The NN means the methyls are on the nitrogen of the amide. We call this DMF. And there's its structure. And again, aprotic. It has no OH bonds. And it's got some polarity, but some non-polarity. So a little bit lower number. Then there is methanol, CH3OH. We've talked about this one before. And ethanol, CH3, CH2OH. Both protic, because they have OHs. And as we said before, methanol, more polar, higher dielectric constant than ethanol, because methanol has a lesser percentage of non-polarity or a greater percentage of polarity, however you'd like to think about that. And here, by the way, if you want to, you can add to that trend by comparing ethanol, methanol, and water. Right? All of those have OH bonds. But water has just a hydrogen. Methanol now has the methyl group. That's a little bit more non-polarity. The ethanol has an ethyl group. That's an even greater percentage of non-polarity. See how the dielectric constants go down as the amount of non-polarity in the molecule goes up. The least polar of our polar solvent group is acetone. There is its structure. Aprotic, no OH. Dielectric constant, 21. Now, if you would like something to think about, why should acetone be significantly less polar than dimethyl sulfoxide? Hint, think resonance. I'll leave you that to think about. Now, everything that we have below this has a dielectric constant of less than 20. So this is why we make that arbitrary division, because it turns out to be convenient. So these guys we're going to call polar. These guys we're going to call nonpolar. So our nonpolar solvents, we have dichloromethane. It's aprotic. It has no OH bonds to it. Then there is tetrahydrofuran, also called THF. That's THF, by the way, not THC. You know, THC, Dunaganjaman. That's, you know, the stuff in THC. The stuff that's, I think we have 6 medical marijuana stores in Westwood now. I think we're up to 6. Something like that. More power to you. If you want to do it, hey, you know, it's your brain, your body. I'm not encouraging it, but you certainly it's your body. All right, here's tetrahydrofuran. It's an ether. It's aprotic, no OH bond. Acetic acid is a carboxylic acid. It's definitely protic. It's got an OH. But here's the surprise with acetic acid. Dielectric constant, 6.2. You might go, whoa, that's got to be a typo. Somebody's immediately probably now pulling out their BlackBerry and automatically submitting their known typos. I found a typo in the lecture. It can't be 6.2. It's got all those polar bonds. It's got an OH bond, a CO single bond, a CO double bond. Shouldn't it have a higher dielectric constant than that? You would think it would. But it turns out that, first of all, dielectric constant really is a bulk property. It's not just a property of one molecule. We can begin to make some estimations by looking at one molecule, but we have to think about like a beaker full of solvent. And in acetic acid, acetic acid, carboxylic acids are so good at hydrogen bonding, they like to form hydrogen bonded dimers. So two acetic acid molecules will come together, something like this. So there's one acetic acid, and here is another one. So they will hydrogen bond there and there. And you see how this dimer, these two molecules, looks kind of symmetric, right? They're like mirror images in a way. What's happening is the dipole in the carbonyl, for example, so the delta plus and the delta minus here, is canceled out by the same thing over here. And you can work through the molecule and compare all the similar bonds and see that they're always pointing in opposite directions. So they tend to cancel each other out. The reason it's not zero is because it's not perfectly symmetric and perfectly frozen. It's dynamic, it's moving around, making and breaking these pairs, etc. But this is, acetic acid is a significantly less polar solvent than we might predict. Then we have ethyl ether down here, kind of like THF, except that in ethyl ether the structure is more flexible, so you can have more circumstances where bond dipoles are pointing in opposite directions. So the dielectric constant is left. And finally, down with hexane, 6 carbons, 14 hydrogens, definitely aprotic because it's only CH, and its dielectric constant is virtually 0 because it's only CC and CH bonds. All right, so these are the solvents that we're going to think about. Now, you might say, okay, this is a table, and like in so many other courses, when you see a table, your first thought is, I have to memorize this. Please don't do that. I mean, you can if you'd like. It's your brain. I'm not going to prevent you from doing it, but I'm suggesting that it's not the best use of your time. What should you know? You should know structures. So, for example, you should know that DMF has this amide structure that we've talked about here. But you don't need to memorize them. Now, if you'd like to put them in flashcards, you can do that. But as you do problems, and there's an SN2 practice problem that says, is this reaction faster in DMF or DMSO? You go, I forget what DMF is. You go and look it up. And eventually, you'll look it up enough times that you'll learn it. It's like your student ID number. How many of you know your student ID number? Right? How many of you don't know your student ID number? Right? You must not be a UCLA student then. Because we don't care about what your name is. We only care about what your number is. That seems to be the way of the world around here. You people. But how did you learn as a freshman or transfer student? How did you learn your student ID number? Every time you needed it, you pulled out your card. And after 10 or 15 times, you didn't have to pull out your card because you knew it. Now, you probably don't know the student ID number of the person sitting next to you because you don't use it. But if you used it, let's suppose you become significant others, and so you swap cards and, you fill out forms for them online and all that other kind of stuff. You need to use their student ID number. Eventually, you learn it because you use it. So it's the same thing with these. When you need the structures, if you don't know it, you go look it up. Eventually, you learn it. The advantage to that, by the way, in learning it that way, is there are some things that you will see more frequently than others. DMF is one, and we're going to talk about why that is. But DMF is the kind of thing because you will see it frequently, you go look it up frequently, and you'll learn it more quickly than other things like, say, diethyl ether down here, which is not a terribly important solvent for SN2 reactions. You should also know the relationship between structure and polarity, which we talked about. You should be able to understand why ethanol is less polar than methanol. If I give you a solvent structure you've never seen before and say, do you think this is polar or not? Go, okay, it's got a lot of nonpolar bonds, not so many polar bonds. It's probably a nonpolar solvent. You should know if a given solvent is protic or aprotic, but that's easy. Look for an OH group. And again, you learn that by doing lots of problems. All right, now we are ready to ask the question, how do I pick a solvent to make my SN2 reaction go fastest? So in this context, we're going to say best. Best is fastest. That's not always necessarily true. Sometimes you need to slow a reaction down, but for our purposes, let's just look for fastest. Now, to do that, we have to think about what would be involved. And the thing that's involved that's going to control the rate is the energy difference between the reactants and the transition state. If we're going to talk about how the solvent's going to interact with it, we also have to talk about charges, because as we said, that's where the stabilization comes from. The interacting of charges on the solvent with the interacting of charges on the reactants and the transition state. Now, we can't draw a conclusion for a single conclusion for all SN2 reactions, because not all SN2 reactions have the same the same charge profile. Most, but not all SN2 reactions involve a negatively charged nucleophile, an electrophile that has no charge, and a transition state then which has a delta minus on the nucleophile and a delta minus on the leaving group. We've seen some exceptions to this. Remember when I was talking about the experiment that proved that backside attack occurred? There was a case where the nucleophile was negative and the electrophile had a positive charge, but that's less common. Negatively charged nucleophile, neutral electrophile, that's about 80 to 90% of your SN2 reactions. So let's start there. So what we want to do to make the reaction go fastest is pick the solvent which provides the least amount, if any, stabilization at all for the reactants, but more for the transition state. Now the reactants are negative and neutral. And as we said, increasing the magnitude of charge increases the interaction. Well, the electrophile is neutral. So it doesn't interact strongly with the solvent. There's some interaction, but at the introductory level, not enough for us to really worry about. For the most part, neutral thing, we can just ignore it. So now we're thinking about the fully negatively charged nucleophile and the transition state with those dispersed, those delta minus charges. We want the transition state to be as far down in energy as possible, and we don't want to do a lot to the nucleophile. Now, the nucleophile is fully negatively charged. The transition state is only delta minus, and this is where the quandary comes in. Because if the nucleophile has a full negative charge, it's going to interact with a polar solvent, say water, with its big delta pluses and delta minuses. That negatively charged nucleophile is going to have stronger interaction with water than the transition state would have with water, where there's only delta minuses. So the problem is, if we say, okay, I want to do the least amount to change the nucleophile's energy, well, the nucleophile interacts with a charged solvent more than the transition state does. So it turns out we can't pick a solvent that makes the transition state, that stabilizes the transition state more than it stabilizes the nucleophile. So let's go in the opposite direction. Let's pick a solvent that does the least for the nucleophile. So if we pick a solvent which is non-polar, we don't stabilize that negative charge on the nucleophile at all, the nucleophile is going to be pretty upset. The transition state, if we don't stabilize it with that same solvent, only has delta minuses, so it just whines a little bit. Here's a way to think about it. Let's see if this metaphor works. I just thought of it. Imagine you have a 2-year-old and a 22-year-old, and each of them has a lollipop. Now, we're assuming for this particular metaphor that it is a mature, well-adjusted 22-year-old, all right? So I'm going to take away the lollipop from the 2-year-old and the 22-year-old simultaneously. Who do you think cries louder? Again, well-adjusted 22-year-old. Who cries? Who is more upset by this lack of stabilization from a lollipop? The 2-year-old, right? Besides, the 22-year-old goes, fine, I'll just go get another lollipop. Or I'll get a bigger lollipop. So the 22-year-old, it can deal with the lack of lollipop a little bit easier. It's still, the 22-year-old's a little unhappy because I took away her sugar, but the 2-year-old throws a hissy fit. So the nucleophile is like the 2-year-old. It is more dependent, going to interact more strongly with that lollipop. If you take away the lollipop, the stabilization, it becomes less happier than the transition state, the 22-year-old, because the transition state with its smaller charges it can deal with them a little bit better. Does that metaphor work? Yeah? Good. All right. So what we want to do is pick a solvent which interacts with the nucleophile even less than the transition state. In other words, we want a solvent which is non-polar as possible. Okay, that's great. That's easy to do. We go to the solvent table and we say, let's pick hexane. That's got the lowest dielectric constant on our list, 1.9. Problem solved. Well, there's a problem. So you go into the laboratory, you take your nucleophile, your electrophile, you throw them in hexane, and nothing happens. No reaction occurs. Why? Because of this dissolving stuff. If your nucleophile is negatively charged, let's suppose it's F minus. A negatively charged nucleophile, always, 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 when you take it out of the bottle, if this is a bottle of F minus nucleophile, it also has something else in it. Along with F minus, it has Right, it has to have a cation. Anions always, always, always have cations associated. And for the reaction to occur, things have to dissolve. How well do you think Na plus, F minus, an ionic solid, dissolves in a completely nonpolar solvent? Remember back to 14C? Remember, like dissolves like. Polar things, ionic things, dissolve best in polar solvents, like water, not hexane. So here is the problem. My negatively charged nucleophile, along with its cation, i.e. an ionic salt, does not dissolve in hexane. So while I have picked the lowest polarity solvent, which should be best for the transition state, the reaction doesn't even occur at all. So you go back to your solvent table and you say, all right, what am I going to pick? To dissolve polar stuff, let me go back to my solvent table. To dissolve polar stuff, ionic stuff, what do I need? I need a polar solvent, like water. But that's bad for the transition state, right? Because if it's really polar, it's going to stabilize the fully negatively charged nucleophile more than it stabilizes the slightly negatively charged transition state. Well, that doesn't help either. So I have a choice. Low polarity, no reaction because nothing dissolves. High polarity, nothing happens because everything dissolves, but the energy of activation is too big. So what do? I'm sorry? Pick one in the middle. That's absolutely right. We compromise. Here's a metaphor. I want to give you a final exam which will absolutely crush your ego. You want a final exam that all you have to do is write in your name and get an A+, right? I know the reality is somewhere in between. We compromise. And I'm not here, by the way, to crush your ego. That's certainly not true. I don't want to do that. I want you to feel good about your studies. So what we do is we pick something in the middle. We pick a solvent which is not too polar. So this is good for transition state, but this isn't good for solubility. So we go up, 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 up. It's getting worse for transition state, but solubility is improving. As we go up now, the solubility improves even more, but the transition state energy becomes too high. So we stop right here in the middle. These four guys, right here, that's the compromise. Polar enough to dissolve ionic reactants, not so polar as to make the transition state unattainable in terms of energy. It's a compromise. So our best solvents are those which are middle-of-the-road polarities, the Goldilocks in terms of polarity. This solvent is too polar. This solvent is too nonpolar. This is just right. Now, what's the other factor? So that's the dielectric constant issue. We want to pick something in the middle of the road. And that, by the way, is, as I said, one of the reasons you'll learn DMF is because it shows up a lot. It's in that group of four. Now, what about the other issue, hydrogen bonding? Well, hydrogen bonding provides stabilization if it's present. The F minus likes to hydrogen bond. It's in the vicinity of something which has an opposite charge, so it makes it feel better. The problem is, if you're in a protic solvent, you have to get rid of some of that hydrogen bonding to react. In other words, let us imagine we're going to do a reaction with fluoride and methyl iodide. So here's the methyl iodide I want to react with. I'm doing backside attack. Right buried in there, you can see it, is the F minus. It's surrounded by a solvent shell of methanols. To react, and there's solvent in the front as well, for methyl iodide and fluoride to come close enough and to react, some of that solvent shell has to go away. Some of that stabilizing effect has to go away. And what happens to energy when you take away stabilizing effect? It goes up. So as the reactants are approaching the transition state and you have to begin to shed some of this hydrogen bonding solvent shell, that's an extra energy price you have to pay to achieve the transition state. Hydrogen bonding is bad for nucleophilicity. Let me give you a metaphor, one of my most famous metaphors. Pick a Hollywood star. I'm sorry? Johnny Depp, good choice. Johnny Depp is F minus. Now, Johnny Depp is going into his favorite restaurant, but he's surrounded by paparazzi, methanol. For him to go into the restaurant, the paparazzi have to move out of the way. Now, I don't know Mr. Depp personally, but if he's like many Hollywood stars, he feels better about himself when the paparazzi are there. He's stable. If you take some of the paparazzi away, he goes, He doesn't feel very good about himself because the paparazzi have gone away. But they have to go away to go into the restaurant. So in other words, if he wants to get this fine dinner wherever he's going, he's got to pay the price of some of his self-esteem, because some of the paparazzi has to move away. Same thing for the SN2 reaction. The nucleophile has to shed some of that hydrogen bonding solvent shell and therefore become a little less stable to react, and that's reflected in the higher transition state energy. Now I'm going to leave you with a question to think about, because this is what we're going to address next time. Do all nucleophiles respond, are influenced the same way by hydrogen bonding? That's where we're going to pick up on Friday, so see you then.